Hey, OChemsters! I blinded you with science today, didn't I? This is Mrs. Vanaway bringing you some OChemster video. So we left off looking at some SN1 mechanisms. We learned that they were done with tertiary substrates. SN2 are pretty much done with primary substrates. But in this section, we want to compare the two, SN1 and SN2, and do a couple examples. And when you're done with this, you'll practice on your own, okay? So the question is, how can we tell whether a particular nucleophile substitution reaction will proceed by SN1 or SN2? And I wrote, hey, why do we care? All right, well, we do need to care so that if you're in laboratory and you're doing some of this stuff, let's say in college in a lab, that if you pick the wrong kind of stuff to do, it's not going to work out very well. You're going to be in lab for a very, very long time. So that's why we care, okay? So here we have the variables. SN2 is the first one, and SN1 is the second one. And so if the halide structure, the substrate, is primary or a methyl group, SN2 is much more faster, it's more common, and it would really be special circumstances to make an SN1 mechanism out of this one. For the scope of this introductory course, it won't, okay? What about secondary? Sometimes. And I circled that because obviously there's more to this than meets the eye to determine if it's a secondary substrate, if it's SN1 or SN2. So we're going to get to that. Well, if it's tertiary, well, I bet you can figure that one out. If it's SN2, very uncommon, again, for the scope of this course, we're not going to worry about it. And if it's SN1, then it's going to be, tertiary. It's going to be very fast. It's very common. All right, what about the stereochemistry? Stereochemistry is about the R and the S and the cis and the trans, okay? So if you have an SN2, you will always have an inversion, R versus S, or cis versus trans. If you have an SN1, it's a mixture. Do you remember why? Because when the halide leaves, the bromine leaves, then the remaining carbons that are surrounding the central carbon there gets to be more of a planar structure. There is no hindrance anywhere for the nucleophile to attack on either the one side or the other side. So it's going to attack 50-50. If it attacks exactly where the bromide left, there is no inversion. So if it started off at R, it'll end up at R. But if the nucleophile attacks from the opposite side, then you're going to have the inversion. You're going to have the, if it started off at R, it will end up as an S. So that's your stereochemistry. So what about your nucleophile? All right, if you have SN2, rate depends on the nucleophilic concentration. If you have SN1, it does not. It only depends on how fast that bromide leaves. Okay, that's it. What about the other one? If you have a nucleophile that is an anion, what does that mean? A negatively charged anion. All right, you're going to favor SN2. If you have a neutral nucleophile, that will favor, again, the SN2, or the SN1, excuse me, the SN1. So let's wrap this up. Plan A, again, for the scope of this introductory course, all right, look first at the substrate. If it's tertiary, SN1. If it's primary, SN2. Okay, that's your first thing. But now what? What if it is a secondary substrate? So the rule of thumb then is look at your plan B. Don't look at your substrate secondary. So remember when I scrolled up here and there you go, I circled sometimes. How do we know? Well, this is how you're going to know. So if it's not your substrate, look at your nucleophile. If the nucleophile is an anion, a negatively charged ion, then go with SN2. If the nucleophile is neutral, go with SN1. So again, plan A, look at your substrate. Primary, tertiary, it'll always be SN1 or SN2. If it's secondary, look at the nucleophile. If it's secondary and it's an anion, look at SN2. If it's secondary and neutral, go with SN1. Okay, so let's keep going. All right, so we've already said that the rate of SN2, not SN1, depends on the nucleophile, and it also depends on the substrate. All right, but the SN1 doesn't care about the concentration of your nucleophile. So if the nucleophile is strong, SN2 would be favored. Well, how do you know if it's strong or weak? Well, first of all, any kind of a negative ion is stronger than any kind of neutral. All right, so hydroxide is going to be stronger than water. This sulfur with a carbon group with a negative charge would be stronger than the one that's neutral. This carbon with oxygen negative is going to be stronger than your alcohol. All right, how else can you tell elements low on the periodic table tend to be more nucleophilic than its elements above them in the same column? So let's look at these guys. So HS is a much stronger, or I wouldn't say much, but is a stronger nucleophile than HO. Why? Because S is lower on the periodic table than the oxygen. And iodine is better than bromine, chlorine, and fluorine. So if you go back and look at the third page, let's go do that real quick. All right, so let's scroll down here. All right, let's look. Which is the only halogen on this page? It's iodine. Why is it iodine? Because it's your strongest nucleophile, all right? Your bromine and your chlorine are more likely to be your leaving group, not the nucleophile. So it's not going to be just a trade-off. Bromine's not going to come and replace another bromine. That's kind of silly there. But an iodine can replace a bromine because it's a stronger nucleophile, because it's lower on the periodic table. Let's go back to the page we're on. All right, so letter C says elements in the same row on the periodic table tend to be less nucleophilic the more electronegative the element. So this carbon with 3 other carbon groups as an ion will be stronger than the nitrogen, which is stronger than the oxygen, which is stronger than your fluorine. Your ammonia is stronger than your water, which is stronger than your hydrofluoric acid. Okay, so like I said, the more electronegative the element, the less likely it's going to be a nucleophile. Not saying it won't be, but the stronger one is less electronegative. Okay, so let's check this out. Again, let me just reassure you, as far as this course goes, not your college course, but this course goes, I'm not really going to make you choose. Let's say if I gave you a secondary substrate and I have you choose between maybe like these two, I'm not going to make you choose between those two and say which ones be more SN1, SN2. That's not the case. I'm going to try to be as consistent as I can. So what does that mean? Well, let me show you in this problem number 1, okay? So it says, which mechanism, SN1 or SN2, would you predict for this reaction? Why? Look at your first thing. Look at your substrate. What kind of substrate is this? Look at the carbon, and how many carbons are off of that? 3. So it is tertiary. So what I'm going to do here, let's look at this. This is what? This is neutral. So you have a win-win situation. You have both, optimal conditions for what kind of reaction? SN1. There is no choice, all right? It is going to be SN1. There's no hesitation, all right? I'm going to try very hard, now that you know, not to give you, say, a tertiary and an anion, like hydroxide, all right? I'll do that, so I want to make sure you are consistent, knowing if it's tertiary and neutral, it will always be SN1, okay? I'll let your college professors deal with what happens if you have a tertiary and an anion, okay? I'll let them worry about that. For us, we're going to keep it as simple as we can. So let's look at letter B. All right, so what would be the substrate here, all right? Well, here's the carbon the iodine is attached to. How many carbons is attached to it? Only 1, therefore it is primary. What is my nucleophile? All right, is it neutral or is it an anion? Well, there's no charge to Mrs. Vanderbilt. You're right, but I see a sodium. All right, so this would actually, be an anion. Why? Because sodium is a cation, making the OCH3 negative. The sodium is a spectator ion. All right, it doesn't really count for any of this stuff. All right, so don't worry about sodiums. So if you see a metal with something, then you know you have an anion here. Okay, sodium, this would be a methanoate. So anyway, what would this be? Well, it is primary, so it's going to be SN2. All right, now watch what happens below. So here is the carbon I am interested in. How many carbons are attached to this carbon? 1, 2. So it is secondary. All right, so ruh-roh, what's plan B? Okay, what is this? I see a sodium, and now I see SH minus. Well, guess what? This is an anion. Why? Because sodium is a cation, making this negative. Okay, so Secondary doesn't help us, so now look over here. What would it be if we have an anion, a strong nucleophile? It's SN2. Okay, it's SN2. Well, let's look at the problem below. All right, so again, this is a secondary. All right, and what is this? Oh, this is neutral. So if this is neutral, what does that favor? It favors SN1. Now, something that we need to be thinking of is also, I didn't really put it in this problem, but let's look at my SN2s. All right, I have an SN2 up here. Now, the thing of it is, do I have to worry about R and S on this SN2? And the answer is no, you don't. Why not? Because here I have 2 hydrogens and then 1 carbon. So I have 2 of the same things. So even though I know there's an inversion, it doesn't show up in the product, okay? But watch what happens with this. Watch what happens. So I'm going to take my hydrogen, and I'm going to call it my A, all right? And then my 1 carbon group is going to be my B, and then the 3 carbon group is going to be my C. So what kind of substrate is this going to be? Is this going to be R or S? Well, let's find out. Let's use it right here. So circle around like this, all right? And what direction is it? It's counterclockwise, so this is going to be an S, okay? What about over here? Well, let's do the same thing again now. My hydrogen is my A, all right? This will be my B, and this is my C, all right? We have a little problem here because we still have the same S. So to be perfectly honest, the way I drew this is not correct. How should I do it instead? All right, I need to reverse this. So I'm going to erase that. And I need my hydrogen to be below. I need my SH to be above. All right, so what am I going to do here? Well, this H I'm going to kind of remove, and I'm going to make this just the H. So now what have I done? So now I have my H is my A, then my methyl group is my B, and my propyl group is my C. So now what? I can make this go in the clockwise motion, and I show my inversion, okay? So when you are looking at SN2, and everything off of that central carbon is different, of a hydrogen, a methyl, and a propyl group, I must worry about R and S, all right? What about up here? Is everything different off of this carbon? I have 2 hydrogens and a carbon. I don't worry about R and S, okay? I don't worry about that designation, okay? So I put in, and I down here, here I don't change it even though I have an ABC going on here. So if this were to be a perfect answer, what else would I do? Well, let me show you. All right, so remember what I'm going to do. Because everything off of that central carbon is different, this is an SN1, this is correct, and so would be the opposite. So if I put the H down here and the OCH3, they both products will happen. This is a 50-50 mixture of this. So once again, I know I'm repeating myself a lot, but I don't want you to be confused. How do you know if you have to worry about R and S? Here's my central carbon, and look what's off of it. I have a 1 hydrogen, I have 3 carbons, and I have 1 carbon. I have 3 different things. I don't count the leaving group. I have 3 different things off of the central carbon. That's your magic number. You need 3 different things that you have to worry about R and S. All right, so if I were to do the same notation with letter D, I would say here my A is on top, my B is over here, and then my C is over here. Wrong way. Well, I'll use it later. Here's my C. Guess what? This is going to be your S designation. If I do the same thing over here, this is going to be my A. If I put my hydrogen on top, this is going to be my B, and this is going to be my C. Well, guess what? That's still the S designation. Here, I'll draw it in. This is still the S designation. Why did I have to put this here? Well, because this is going to be what? A, hydrogen, there we go. So B is my 1 carbon, and C is my 3 carbons. So how do I designate this now? Go A, B, C, and that is my R. So I have an S and I have an R, 50-50 mixture, okay? So what I did is I created 2 more problems for you. Aren't you so lucky? So I have a letter E here. All right, so what do I have here? Clearly, I used something with a branch off the cyclohexane. So I can be thinking of cis and trans, all right? If there was no methyl group off of the cyclohexane, there's nothing to worry about, okay? There's no R and S, cis and trans, no nothing, all right? But if I put a methyl group on the opposite of the bromine, I have a trans going here. So what kind of carbon is this one right here? Well, here's a carbon with 1 carbon, 2 carbons, and a hydrogen, don't I? It is a, oops, come here. It is a secondary carbon. Ruh-roh, well, now what do I have to worry about? Well, what is this? Is this an anion or is it neutral? Well, folks, it is neutral. So what kind of reaction is this? SN1 or SN2? Think about it. Secondary and neutral. What's it going to be? It's going to be an SN1. All right. So what do you have to worry about SN1? How many different products are you going to make in this situation? Well, if this is trans, what am I going to make? Well, half of it's going to be a trans. What else? Oh, that's right. I'm also going to have a cis. So it's 50% trans and 50% cis, and I still have an H plus that came off in a Br minus. Why is that? Well, the H here, remember, if I put a neutral nucleophile on my cyclohexane, it's going to be a positive charged organic product. But what happens at the H of the alcohol is going to come off, and that's this H here. Okay, so because it's SN1, you have to worry about, oh, I got 2 different products. Okay, I have 2 different products. So look at my next one, and then I'm done. All right, so take a little time and draw the structure again. It's the same one from above, but what did I change? Well, my nucleophile is now a what? It's an anion, isn't it? And it's still secondary over here. So what kind of reaction is this going to be? SN1 or SN2? What do you think? It is SN2. So now what? If this is trans, how many products am I going to have? It's SN2. How many products am I going to have? You only have 1. Why is that? Because you don't get a carbocation as a intermediate, okay? This is where you have bromine comes off as the hydroxide comes in from the back side of the bromine. All right, so if anything, the hydrogen is sticking straight down, the hydrogen that was here to begin with. So this is 100% cis, all right, and don't forget you get the leaving group, okay? So I'm really hoping that this helps. If you need to, watch it again if I went too fast or something like this. And let me leave you with one more thought. Science rules. Don't wait to be great. We'll see you next time. Bye-bye.